Hello, my name is Manat Saluja, and this is my master's thesis implementation. So, the title is AI-based hybrid fault tolerance framework for cloud data centers. So, technically, cloud data centers are the backbone of the modern digital infrastructure. Every day, they run millions of virtual machines handling the critical workloads of AI banking systems, healthcare problems, e-commerce services, and many more. So, when a server fails unexpectedly, the consequences are service downtime, data loss, and the significant financial costs. Yeah, so the traditional fault tolerance is reactive. The system waits for something to break, then scrambles to recover. My work asks for the different question. What if the system could predict a failure before it happens and take preventive action automatically? So, this project builds exactly that, a proactive AI driven fault tolerance framework that uses a deep learning LSTM model to detect the impending failures with over 99% accuracy and then automatically triggers VM migration and selective replication to keep services running without any interruption. So, the system is organized into the five layers, all running together on a real AWS EC2 instance in the US East Region 1. So, at the top, I would say first, let's go to that. Mm, so, the system is organized into the five layers, all running together on a real AWS EC2 instance in the US East Region 1. At the top, first, let's go to this. Yep. Mm, yeah. So, at the top is the user layer. This exposes a REST API and a live web dashboard that clients and the operators could interact with. So, below that is the cloud controller layer. It contains the API gateway, a task scheduler that routes incoming workloads, a resource manager that tracks any server capacity, and a monitoring system that continuously watches the server health. The heart of the project is the AI fault prediction layer. This one. So, this is where the LSTM model runs in the background, continuously analyzing the real-time server metrics through a sliding window of the last 10 time steps and predicting whether a fault is imminent or not. So, when the model detects a high prediction, it signals the fault tolerance layer, which contains four response mechanisms: virtual migration to move the workloads of a failing server, selective replication to duplicate critical tasks on a healthy servers, an energy aware scheduler that balances the load to avoid the overstressing any single machine, and a recovery manager that handles all the post fall cleanup and service restoration. So at the bottom, mm, sorry for that. Yep. So at the bottom, there is a physical data center layer representing the actual or simulated the server being managed. All the five layers communicate through a shared in-memory server registry and the Python function calls, making the system fast and self-contained. Yep. So now it's the data pipeline. So let me walk you through the data pipeline. The training data comes from the real Kaggle virtual machine workload dataset containing 1,35,873 rows of the performance metrics across the 14 virtual machines. So let's move on to the code now. Yep. So now I'll write one command. So basically, what it's doing, this is loading the raw workload CSV files from the dataset folder and consolidates them into a single structured data frame saved to the raw data. So this dataset captures the 5 key metrics per virtual machine. So what are these? It's the CPU utilization, memory usage, disk read throughput, disk write throughput, network input and output. Next, we will run the preprocessor. And now I have that already. Hmm. Yes. So the preprocessor does three very important things. First, it normalizes all the 5 metrics to 0 to 1 range using the minimum max scaling so that the LSTM can run across all the features equally. Secondly, it applies a fault injection, labeling sequences where CPU and the memory usage ramp get ups, plateau at the high load, and then drop. Simultaneously, sorry, yep, and then it drops, simulating 13.2% fault rate across the dataset. Again, thirdly, it applies a sliding window of the size 10, meaning each training sample is a sequence of 10 consecutive time steps, which gives the LSTM the temporal context it needs to detect a fault trend. So, the output is 6 NumPy arrays and it's saved to the data process X and Y splits for the training validation and test sets ready to be fed directly into the model. So now let's get on to the model training thing, and we can train the fault prediction model here. So let's move on to the code for that. Yep, here it's a code, and now I'll run a command here. So basically I run a command to do the fault prediction training there, training for the model of the fault prediction. So this model is basically a multi-layer short-term memory network, an LSTM, which is a type of some recurrent neural network is specifically designed to learn the patterns in the sequential time series data. So this makes it ideal for a use case where we need to detect a failure trend unfolding over multiple steps. The architecture detect a failure trend unfolding over multiple time steps. The architecture has an input of 5, or I would say 1 value per metric per step, a hidden layer size of 128 units, 3 stacks LSTM layers, and a dropout rate of some 0.3 to prevent the overfitting. I'll give you, I'll show you the threshold logics there. That's what I'm talking about. So the final output is passed through a sigmoid activation to produce a fault probability between 0 to 1. We use a fault threshold of 0.5. Any prediction above that triggers a fault alert. For high confidence faults above 0.75, the system also activates the selective replication as an additional safety measures. So as training, we have to go to the code again for that. So yeah, as a training, we can see the loss decreasing each epoch. So we are just at 1 right now. It will take a lot of time to go till the 50. So I'll just tell that verbally. So the model was trained on a GPU and NVIDIA RTX 5090. So training completes quickly. Once it's done, the training weights are saved to the model's fault predictor.pt and they are ready for the interference. With the model trained, we evaluate it on the held out test set and the data model has never seen during the training. So now I'm going to show you the code for the model evaluation there. So yeah, That's a code for there in which we have mentioned all the threshold. I explained it in the earlier part. And now I'm going to run a command so that we can see the all accuracy, precision, recall, F1 score in all one table. Sorry, I guess I have did some mistake. So now it will show some like a table with the like numbers for the accuracy, precision, recall, F1 score. Yep. And now we can see the whole analysis for it. So these results, they are outstanding. The model achieves around 99.58% accuracy on the test set. Precision is 99.10%, which means that when the model raises a fault alarm here, it is correct 99.1% of the time. Very few false alarms that would waste resources. Recall is for 98.75%. The F1 score of the 98.92%, that balances both of them here. And confirming the model performs consistently well across both the classes. So these results significantly outperform traditional threshold-based reactive approaches. In a comparative baseline study, a reactive system with no prediction showed an average fault recovery time of the several seconds and higher resource. So our proactive system reduces the recovery overhead dramatically by acting before the failure fully materialized. The evaluation also generates a confusion matrix or the accuracy loss curves, all the save to the results, plots and directory. So now we can head towards the next suit execution. We are onto a test suits now. So to ensure the correctness across each layer of the system, the project includes a comprehensive test suites organized into a unit test, integration test and the performance test. So now again let's move on to the core. I'll walk you through that. It's there. Yep. No, sorry. Yeah, this one. So we can move on through our code and I'm again gonna run one command. So it shows that all of the tests which have been done, they are passed away. So basically, the unit test, it covers each module in isolation. The test model.py file verifies that the LSTM forward pass produces the correct output shape and that prediction falls between the 0 and 1. So the test processor.py files verify that the normalization is applied correctly and that the sliding windows are formed with the right dimension. Test VM migration.py, test application manager.py. We can see that all of them here. And the fault tolerance mechanism with the control inputs. So the integration test, it verifies that the full pipeline works and to end, and test prediction pipeline.py checks that the data flows correctly from raw input in all the way through to the fault prediction there. Test false tolerance flow.py confirms that the predicted fault correctly triggers migration or the replication. So the test API here, endpoints.py, verifies it all the HTTP points are return and correct status codes and JSON structures. So the performance test basically measures API response time under the repeated request to ensure the system remains responsive under load. So here we can see that all the tests has passed, validating all the complete implementation. So now we can move towards our live system and the dashboards. So we can move on to our browser for that, which the whole system is on deployed. demo run, which is the system is all deployed on the AWS. So I'm going to show you that. So I have to run the command for that. So yes, it's that system which is deployed, as I told before, on the EC2 T3.micro instance. And I'm going to show you that the live web dashboard and the API ends. So this is opening here. It will take few seconds to go there. Yep. So now we are here. So this endpoint basically returns the current state of all the managed servers, showing the CPU usage, like the memory load, health status, and whether any fault alert is active here. This returns, like we can see the predictions here, the accuracy and everything. The fault predictions. These are the servers running, and some servers are quarantined here, some are healthy, they are the fault predicted. There are around a lot of results here. So this basically returns the most recent LSTM fault prediction for each server, a probability score and a binary fault flag. So this submits a new task to the scheduler. The system evaluates the server health, routes task to the healthiest server available. You can see that here as well. Yeah. And if there is any server that shows a high fault probability, it automatically triggers VM migration or the replication to protect the workload. So finally, the metric summary endpoints returns the aggregated performance statistics, model accuracy, average response time, and the fault event counts useful for the ongoing monitoring and reporting. So now we can move to we did that API demonstration as well. And now we are heading towards our deployment and the CI/CD part. So now the deployment is fully automated through a GitHub Actions CI/CD pipeline. Every push to the main branch triggers a 7-step pipeline. Step 1, 5, run all the test unit integration and the performance in a clean environment. So if any test fails, the pipeline stops and the deployment is blocked there. I'll walk you through the code for it. Sorry. So it is the main code for that. And the step 6 is there, which is like connecting the SSH into the EC2 instance using a stored private key secret, performs a git pull to get the latest code, runs pip install to pick up any new dependencies and restart the system services, fault tolerance application service, which manages the Gunicon process. So step 7 performs a healthy check as it sends a GET request to the metrics summary endpoint and expects an HTTP 200 response. Right. So if the application is not responding, the pipeline flags a deployment failure. This means every code change is automatically tested and deployed to the production without any manual steps, ensuring the live system is always running the latest validated version. Now, I'll show you the whole GitHub setup for that. Yeah. So our whole setup, like first I'll show you that. Yep. This is my whole project, my whole code is there, and there are the GitHub actions which I showed that they all are done here. And now we can move towards our summary, conclusions, and the key contributions. We have done this and the key contributions. Here we are. So to summarize, this project delivers a complete production deployed AI-based fault tolerance framework for the cloud data centers. So the key contributions are: first, let's see, a proactive fault prediction system using an LSTM model trained on a real VM workload data, achieving this much percent accuracy and this much percent precision and that percent recall, which I have showed before. Secondly, a full fault tolerance layer with the 4 automated response mechanisms, virtual machine migration, selective replication, energy aware scheduling, and the structured recovery management. Third, a live publicly accessible REST API and a web dashboard deployed on the AWS EC2 with the Nix and Gunicon service real traffic, which I have already showed before. Fourth, a complete automatic CI/CD pipeline which ensures that every code is changes to the tested and deployed without manual intervention. Last, a comprehensive test suite with the unit integration and performance tests validating every layer of the system. So this work demonstrates that moving from a reactive to proactive fault tolerance is not only feasible, but they are highly effective, and that deep learning models like LSTM can be deployed in the real cloud infrastructure to provide intelligent autonomous system protection. So thank you for watching.